After we have learned how objects roll and how the speed of a sliding block compares to the speed of a rolling object, let's now learn about the main factor that controls the speed of the center of mass of rolling objects. As an example, we are going to compare the speed of a uniform solid disk to the speed of a hollow disk. Remember that the moment of inertia for a solid disk is equal to 1/2 mr squared, where m is the mass of the disk and r is its radius. On the other hand, the moment of inertia for the hollow disk is equal to mr squared. Notice that the moment of inertia for the hollow disk is larger than the moment of inertia for the solid disk, and this is due to the fact that the mass in the hollow disk is distributed far away from the main axis of rotation. Regardless which object you use, there are three forces that will act on it while it's rolling down an inclined plane. The normal force is always perpendicular to the surface of contact. The weight mg is always pointing straight down. And finally, the static friction force, which is parallel to the surface of contact and acting up the inclined plane. The work done by the normal force is equal to 0 because the normal force is perpendicular to the displacement at all times. The work done by the static friction force is 0. As stated in the previous video, the static friction force does not do any work. As a result, the work done by the non-conservative forces equal to 0. This condition allows us to use the conservation of energy principle, where the kinetic energy initial plus the potential energy initial, which is the top of the incline, is going to equal the kinetic energy final plus the potential energy final, which is going to be the bottom of the incline. Since the objects are going to be released from rest, therefore the initial kinetic energy is going to equal 0. The potential energy is going to equal mgh initial. The final kinetic energy is in two forms: the translational kinetic energy, which is 1/2 mv final squared, plus 1/2 I omega final squared. The potential energy final is going to be 0 because we are going to use the bottom of the incline to be the reference point of measurement for our heights. Notice that the total initial energy is in a form of gravitational potential energy, which converts at the bottom of the incline to kinetic energy. As stated earlier, this kinetic energy at the bottom of the incline is in two forms: translational kinetic energy and rotational kinetic energy. The amount of rotational kinetic energy clearly depends upon the moment of inertia. Therefore, the larger the moment of inertia I, the larger the rotational kinetic energy, and the smaller the translational kinetic energy is going to be. Since the translational kinetic energy is directly proportional to the square of the speed, this causes the speed to decrease and the object therefore start to move slower. Now that we have proved the idea conceptually, let's prove it mathematically. In the case of the solid disk, the kinetic energy, as stated, is equal to 0 at the top of the incline. The potential is mgh initial. The kinetic energy is in two forms: translational, which is 1/2 mv final squared, plus the rotational, which is 1/2 times the moment of inertia for the solid disk, which is 1/2 mr squared, times the angular velocity final squared, which equals to the speed final squared divided by the radius of the solid disk squared, plus 0 potential at the bottom of the incline. Notice that the radius squared is going to cancel out. Notice also that the mass is a common factor, therefore it cancels out. And this equation is now simplified to the following. The gravity g times the height initial equals 1/2 times the v final squared plus 1/4 times the v final squared. gh initial equal, notice that 1/2 plus 1/4, that's 3/4, v final squared. Isolating the v final, we obtain square root of 4/3 gh initial. And this is the mathematical expression for the speed of the solid disk at the bottom of the incline. Now, let's evaluate the same speed for the hollow disk at the bottom of the incline. The mathematical expression that we have obtained from the conservation of energy was 0 plus mgh initial equals the translational kinetic energy final plus the rotational kinetic energy final plus 0 potential at the bottom of the incline. Simplifying this equation the same way we did with the solid disk, the left hand side is going to be the same as before, which is mgh initial is going to equal 1/2 mv final squared, which is the translational kinetic energy, plus 1/2. The moment of inertia for the hollow disk is equal to mr squared. The omega final squared is equal to v final squared over r squared. As before, notice the r squared is going to cancel out. The mass is also a common factor, therefore it cancels out. And this expression is simplified to the following. gh initial equals 1/2 times v final squared plus 1/2 times v final squared also. This can be simplified further. gh initial equals 1/2 plus 1/2, that's 1, therefore equals v final squared. Isolating the v final, we obtain the square root of gh initial. First, notice that the mass and the size of the rolling objects are completely irrelevant because both the mass and the radius did cancel out, and the speed v is not related to them. The other conclusion, which was stated earlier, which is about the speed of the rolling objects at the bottom of the incline, notice that the speed of the solid disk is square root of 4/3 ghi, whereas the speed of the hollow disk is the square root of just g times h initial. Therefore, the speed of the solid disk is going to be larger than the speed of the hollow disk at the bottom of the incline. The final conclusion is the larger the moment of inertia, the slower the objects are going to roll.